This video will demonstrate how to use the work-energy theorem to solve a problem. The problem statement is as follows. A car with a mass of 1,100 kilograms is traveling at 30 miles per hour when it has to suddenly stop. If the brakes apply their maximum force, the car will stop over a distance of 15 meters after the brakes are applied. We are first asked, what is the kinetic energy of the car before the brakes are applied? Then we are asked, what is the maximum force the brakes can apply to come to a stop? And finally, we're asked if the car is instead traveling at 65 miles per hour, how far will the car travel after the brakes are applied given this maximum force? Well, of course, the first step in our problem-solving process is always to write out the data that we are given. And for the first part of this problem, we are told the following, that the mass of the car is 1,100 kilograms, and that the initial velocity of the car is 30 miles per hour, and that the stopping distance is 15 meters. Those are the pieces of data that we are given in the problem. Now we can immediately see one problem with our data in that the units for velocity are not what we need. We need meters per second, not miles per hour. But this is a problem that we have dealt with before. We first convert the miles into meters using the conversion factor 1,609 meters per mile. And then we convert the hours into seconds using the conversion factor of 3,600 seconds per hour. That gives us an initial velocity of 13.4 meters per second. Now notice that I have left this in 3 significant figures, despite the fact that the problem is 2 significant figures, just keeping that extra significant figure to try to minimize rounding error. Well then, the answer to the first question can now be discovered because we can tell that the initial kinetic energy is going to be 1/2 times the mass times that initial velocity squared. So 1/2 times 1,100 times 13.4 squared, and the initial kinetic energy is 98,900 joules. Very high number, but remember, a joule is a very small unit. So that's our initial kinetic energy. Our final kinetic energy is going to be 0 because our final velocity is going to be 0. We come to a stop. That means the change in kinetic energy, in other words, KE final minus KE initial, is going to be negative 98,900 joules. Now, while a value for kinetic energy can never be negative, this is a change in kinetic energy, and so we essentially are saying that the car loses 98,900 joules of kinetic energy. That energy is transformed largely into sound and heat, which then spreads out into the environment. Well, the work-energy theorem tells us that the change in kinetic energy is equal to the work done by all forces. The work done by all forces, and in this case, the only force doing work on the car is going to be friction. So this is essentially the work done by friction. The friction in the braking system. So that's going to be negative 98,900 joules. That's going to be equal to FD cosine theta. Now theta is going to be equal to 180 degrees. because the force stopping the car is in the opposite direction of the car's displacement. If the car is moving forward, this force applied by the brakes is going to be backward. And that means the cosine of theta is going to be -1. The stopping distance is going to be 15 meters. So we plug that in there for the distance. And this gives us a final force of 6,590 newtons. We would report this maximum braking force as 6,600 newtons because the problem has two significant figures. So this is the maximum force that the brakes can apply. For the faster speed, we retain that maximum force, and so we must recalculate the stopping distance. Therefore, we have a new initial velocity, which is going to be 65 miles per hour. We do the same procedure as we did previously to convert that miles per hour into meters per second, and we get that 65 miles per hour is 29.1 meters per second. That means the new value for the initial kinetic energy is going to be 1/2 times the mass, 1,100 kilograms, times 29.1 meters per second squared. The new initial kinetic energy is going to be 466,000 joules, again keeping the extra significant figure. You can see that's an awful lot more kinetic energy. In fact, it's about 5 times more kinetic energy, so that's going to have a dramatic effect on the braking distance. The final kinetic energy is still going to be 0. So in this case now, our change in kinetic energy is going to be negative 466,000 joules. That's going to be equal to the work done by friction. So that's going to be, once again, FD cosine theta. Once again, theta is 180 degrees, so that cosine theta is -1. The negative signs cancel as they did before, and so we're left with this. The maximum force we're going to bring over from the previous problem, because that is the maximum amount of force that the brakes can exert. They can't do any more than that. And so we can calculate our new braking distance, and we find that new braking distance to two significant figures is 70 meters. Let me point out that this is just the braking distance. This is assuming an automatic reaction by the driver and an automatic reaction by the braking system. In reality, it would take time for the driver to react and time for the braking system to react, and that would only add to these distances. So this is merely the distance during which the brakes are applied. The total stopping distance will be longer than 15 meters for 30 miles per hour and longer than 70 meters for 65 miles per hour. But the general idea here is that a greater velocity